Hello everyone, so now I will show you how to solve this Airfoil problem by using the other solver. So previously I uploaded one video and I used CFX. So there is another tool, this is FLUENT, and so we usually use FLUENT. So FLUENT is a method we usually use the finite boolean method, so you can use the FLUENT to solve this problem. So what I did, I just dragged this FLUENT and connected with this too. So when you upload the mesh and when you will connect the FLUENT, you can see this portion is not updated, so you need to click on update project and it will take a bit time. So once it's updated, you can go to the setup, okay, and you should select the double precisions and maybe the serial processing options, and as the model is 3D, so it will automatically choose 3D. So click on OK. So once you click on OK, you can see it's working now, and yeah, and you can say this is steady. You can select a steady or transient, but today will show only for the steady. So select the steady. If you want, then you can check the mesh from here. So if you click on mesh, then it will show you the different qualities, yeah, the stats and the minimum maximum volumes, face areas, everything. So you can see it from here. So go to the model and we'll deal with the laminar pros. So keep it is laminar. There are different models, so I'll discuss maybe in my next video. So just select laminar, and the materials, you can see that this is air. So air is one of the materials. So if you want the properties for air, you can do it from actually the air density it should be 0.225. I changed it previously. So if you want to change the materials, so you need to just write it down here and then click on change. So it will change, then close it. So if you open it again, then you can see this is the new hello. So in that way, if you want to change the material properties, you can do it from here. You don't need to think about the cells and conditions for this case. Now the important thing is the boundary conditions. So when we did the mesh, we already named all of these parts, but in CFX you need to do it again. So what it came to from here is, if you want to see the boundary parts, then you can click on highlight zones. So suppose we want to see this part, so click on the airfoil. So you can see this is the airfoil, right? If you want to see the inlet, so you say this is the inlet. Anyways, so now we will set the boundary conditions for inlet. Suppose the velocity is 5 meters per second. This is the velocity magnitude, and it should be the magnitude normal to boundary directions. The outlet, we will put the outlet pressure is 101.325, and so the top, this is the wall. So this is the symmetry, so we'll select this, the symmetry, the boundary conditions, and the bottom, now it's all, so we'll say this is symmetry. The front, we'll say this is norm, this is symmetry, and back, this is also symmetry. And the airfoil, definitely this is wall. It is a stationary wall, it's not moving, and then I'll select boundary conditions. Click on OK. Oh, we don't need to think about the dynamic mesh, because yeah, we usually use it is a deforming body. So if it is deforming body, then we usually use this, so you don't need to think about that. Reference value, you can select, calculate from inlet. The solution method, there are different methods, so you can use this is maybe the couple physics or listen. For this case, all of this is second order pressure, momentum conditions. For the monitor, this is important. So the default value actually is 10 to the power 3. I changed it earlier, so it should be 10 to the power 3. So when you will open this, you will see this is 10 to the power 3. So for this case, we'll use the default value. So this is the continuity. I will explain it work and why it is important. So click on OK now. You don't need to change all of this, the solution initializations. When we use the complex asymmetric model or the tetrahedral elements, we usually use the hybrid initializations. So click on initialize, and then you can see it's working, it's initializing, checking the topology. So it's done. Solution calculation activities, you can, if you want to save after 10-15 iterations, you can select how many iterations you need, then you can put it here. So go to run calculation. So maybe we will run this problem for 100 iterations. So click on calculate, and now wait. So yeah, so this is the scaled residual. You can see it's stated solving. This white line, this is for the continuity, and this is the XYZ velocity. So you can see this line is going down, and we said the residual condition is 10 to the power 3. So when we will see this white line, you can see all of this tray, it's already touched this line 10 to the power 3, and it is far away from this point. So when we can see that this white line just touches this 10 to the power 3 value, then we can say that solution is converged. So it will take time. So I'm not running the solution until it reaches the convergence, but when you will run your simulation, you have to wait until this white line it touches this point, and for the steady case, when it is converged, the solutions automatically stop. So it will show you, okay, solution completed. So now I'm just stopping these solutions here, but we can say it's yeah, sometimes it's fluctuating, but you can see this value is decreasing, increasing a bit more. So yeah, it's now fluctuating. Still it's not stable, you can see it's decreasing. So still it's not into the power 1. So you can see now it's into the power 2. So that means it's going down, and it will take time to reach the convergence. So I'll stop it now, and you can see solution completed. But you need to run this simulation until it does that